We want to show the interconnection between statistics and geometry. Do you see that standard deviation is a distance, and L2, Euclidean distance, and correlation coefficient is inner product? Let's find out. Let's begin with the fair coin flip. Suppose you get 1 when you flip head and 0 when you flip tail. So you have two equal probability outcomes, 1 and 0. Let's use a two-dimensional point to represent this random thing, 1, 0. By the way, what if the coin is not fair? Say 2/3 of the time you flip head, 1/3 you flip tail. In such a case, consider a three-dimensional graph with our point being 1, 1, 0. That makes sense? Now, let's find out its mean point. The point that represents its mean. It's gotta be 1/2, 1/2, right? It means another coin flip where you always get 1/2 no matter what you flip. So the mean point must be in the form of x bar, x bar. Each element stays the same. Meanwhile, it must also satisfy the sum of all elements equals the sum of our original coin flip point, which is 1 plus 0 equals 1. Now we have it. To find the mean point, we solve for two sets of equations. The first set, all elements are the same. That actually consists of n-1 equations. So in an n-dimensional space, it defines a one-dimensional straight line right here. We call it central line, since all points on this line are the so-called mean points of some random variable. The second set of equation is the sum of all elements stays the same as our original point. That is only one equation. In the n-dimensional space, it defines a n-1 dimensional hyperplane. The intersection of the central line and the hyperplane is then the solution of a total of n equations. So it can only be a zero-dimensional point, our mean point. Here's a proof left for you. The central line and the hyperplane are perpendicular to each other. Now our standard deviation, at least a main part of it, is exactly the Euclidean distance between these 2 points, isn't it? Since the hyperplane is perpendicular to the central line, our standard deviation is also the distance between our original point and the central line. So what does central line mean? Central line means there's no randomness. The closer a point is to the central line, the less randomness or less variation our random variable is. The farther it is, the more variation your bet is, right? And our mean value is also a kind of distance, isn't it? It is the distance from the origin to our hyperplane. The hyperplane are all the points where our sum stays the same, right? So the farther our hyperplane is from the origin, the larger our average return is. But wait, how to explain the square root of 1 over n? Well, we have 3 ideas, and it's up to you to decide. The first idea, we need square root of 1 over n to balance the increase of dimension. Think of it. The length of the diagonal of the two-dimensional square is square root of 2, right? And the same thing of the three-dimensional cube will be square root of 3, and so on. So, with square root of 1 over n, you'll get the same result if you complicate our coin flip into a fourth-dimensional with 1, 1, 0, 0, giving each outcome a quarter of chance. That still represents the same coin flip, right? Yet it goes to a 4-dimension. The second idea is from probability. If you think about it, 1, 0 is not a solid point. Each element only appears 1/2 of the time, right? So consider it half solid, with the twin 0, 1 also existing half solidly. This is a more philosophical explanation. The third idea is simply ignore it for now. Why? Because we're going to call this distance on the central line means or differences of means. You see here, we also dropped a square root of 1 over n on the mean line, on the central line. Why we do that? Because they do cancel out when we divide our mean by standard deviation, when we do statistical tests. Now let's talk about covariance. We are considering two random variables. We better use a three-dimensional space, if not higher. In our simple case, random variable 1 is represented at 1, 0, 0, and random variable 2 is at 0, 1, 0. Here you see the central line, the hyperplane, and the mean point. Now we find two vectors from the mean point to the representing points of the two random variables. Covariance is defined as the inner product of these two vectors, with square root of 1 over n overlooked again. Hope you can see that. A more commonly used concept is correlation coefficient. That is the standardized inner product of the two variables, each divided by its own length before doing inner product. And what does inner product of two standardized vectors mean? It means the cosine of the angle. If they go in the same direction, the cosine and hence the correlation coefficient is maximized. If they are perpendicular, the cosine or the correlation coefficient will be 0. If they go in the opposite direction, it'll be -1, right? Now we have the geometric view of mean, standard deviation, and the variances. It's time to play with them and develop our geometric view of some of the most commonly used statistical tests. First, t-test. In a word, t-test determines if the means of two sets of data are significantly different. We know virtually everything is different. So how do you say it's significant? You will have to consider their standard deviation.
It's all relative.
A 5-inch difference in height could be significant for human brothers, but it won't be for whale brothers. Therefore, the so-called t-statistic is defined as the difference of mean divided by standard deviation. There are multiple scenarios, adjustments of square root of n, and pay attention to degree of freedom. But for now, let's focus on this geometrical intuition. The simplest case is to compare against a constant. First, we find the point on our central line for the constant, because it compares against our mean. And here's our point that represents our sample. In the same way as before, we'll find the mean point on the central line for our experiment. So this is the difference of the mean, and this is the standard deviation. The t-statistic is simply that divided by that, right? And since these two lines are perpendicular, our t-test basically calculates a tangent of the angle, isn't it? And here's the intuition. If it's like this, the difference of mean is relatively small, so we say there's no significant difference. If it's like this, the difference of mean is relatively large. We will say the difference is significant. Let's quickly go through the scenario of comparing two samples. We have two original points, two mean points, the difference of mean, and two standard deviations. Let's look at the denominator. It is square root of sum of squares. Isn't it another Pythagorean theorem? There's got to be another right triangle. And it's here. Wait a minute, how is it a right triangle? This two-dimensional plotting is misleading. With two samples, each for the two observations, is actually four-dimensional. By assumption, the two samples are independent. So these two lines are perpendicular. Let's rotate the space, and now you'll see the right triangle. And that's our t-test. Finally, let's talk about a quite misleading thing in statistics, ANOVA, analysis of variance. is misleading because it still determines if multiple groups of samples share the same mean.
No!
It's still about mean, the same as t-test. The only difference is that it works with multiple samples. In the case of 3 or more samples, we can't directly compare two mean points by just subtraction. The concept of how close multiple points are will be, yes, variance. Now let's visualize. We have 3 groups here. Each has its representing point, mean point, and standard deviation or variance. Now we go higher. The 3 mean points will find their mean point. Of course, it's a weighted mean point. Now, in the new space, they find the overall mean point. Moreover, the overall mean point is also the mean point of all the individual samples taken out of groups, right? Now, this point that represents all samples, obviously in a higher dimension, will connect to the same overall mean point in that high dimensional space with the same operation of finding mean value, right? So both are perpendicular to our central line. Finally, let's connect these 2 points. We have a final triangle. First, the square of the length of this line is the sum of all variances within groups. Why Pythagorean theorem? Let me leave it to you. Next, the square of this length is the variance of these 3 group means. So it's called sum of squares of treatments. And finally, that is sum of square of total, right? All samples individually to their mean. And at all last, this is a right angle. Why? Treatments and variances within groups are independent by definition. Now you know the name of this classical relation. Yes, Pythagorean theorem. And finally, our F statistic looks like this. Again, a tangent, right? Or maybe a square of a tangent. Now it's time for intuition. If it's like this, the sum of square of treatments feels relatively large. We'll say there is significant difference. If it's like this, sum of square of treatments feels small. We'll say no significant difference. Hope it makes sense. Thanks for watching.